All right, welcome general chemistry students. This is the second video in week 11 and we are still exploring this idea of the integrated rate laws. In this video, we're going to be looking at if I have a set of data, how do I determine what the rate law of the reaction is? Okay, so by the end of this video, you'll be able to use a graphical method to determine the rate law. And we're just really looking at the simplest cases, 0, first, and second order rate laws. And you'll also be able to use that information to calculate half-lives. All right, so let's get started. So let's review what we saw in the first video. So we saw that if I have a 0 order reaction and I plot the concentration of the reactant versus time, I should have a line, right? And the slope here is minus the rate constant. If I have a first order reaction, then I can plot the natural log of the concentration versus time. And when I do that for a first order, I have a line where the slope is again minus the rate constant. For a second order reaction, if I plot 1 over the concentration versus time, it's linear for a second order reaction and the slope here is K. So with all of those things, what we're doing is we're plotting the concentration versus time, the natural log of the concentration versus time, and the inverse concentration versus time to determine what our reaction is. Is it 0 order, first order, or second order? Okay, so that's what we're going to do. All right, so imagine I have this reaction and it's first order, and the rate constant is given as 2.9 times 10 to the minus 4. Find the concentration at 865 seconds when the initial concentration is 0.0225 molar. So here we're going to use the integrated rate law. And so a clue here is time. Any time the time is included here, you know that you need to use an integrated rate law because the integrated rate laws include the time of the reaction. Okay. Another clue we have is that, okay, so it's first order. So we have time, we have first order, we know we're going to use the integrated rate law for a first order reaction. All right, and we're given some concentration, we're given time, and we're given a rate constant here. So we're going to find the concentration of SO2Cl2. All right, and our relationships here are that we know it's a first order process because that's given, and we can use the integrated rate law for a first order. And really what we're doing is we're just plugging in those numbers. So we want to know what the concentration of SO2Cl2 is, but first we need to plug in our numbers. So we know what our rate constant is, we know what our time is, and we know what our initial concentration is. Okay, and when we solve that, we're left with the natural log of that concentration is equal to negative 4.04. To solve for a natural log, remember the natural log is a base e, all right? It's a base e, or exponent. So we're going to take e to the negative 4.04 to give us the concentration of our SO2Cl2. Okay? Important to remember that natural log has a base e, so we're going to take e to that power to solve. All right, and so it says here that we should check our answer. So we would expect that if this is a first order reaction, over some amount of time, that concentration from the initial concentration should decrease. And what we see is we go from 0.0225 molar to 0.0175 molar. So we do indeed see that the concentration is less, and that's what we should see if we did this correctly. All right, now we're going to practice yet again. So we have a reaction of Q going to 2R. All right, so in this case, we are second order in Q. If the initial concentration of Q is 0.01 and we have 500 seconds, the concentration of Q equals 0.001. What's the rate constant? All right, so how do we know we use the integrated rate laws here? Well, we know because we have time. Okay, so that should be your clue. We have time, so we can use those integrated rate laws. And we also know we have second order, so that means we can use the integrated rate law for a second order reaction. All right, so what do we know? We know the concentration initially. We know the concentration after some amount of time. We're going to find that rate constant. So we're going to use the equation, the integrated rate law, for a second order reaction. All right, so really this is a matter of plugging in those numbers. So we know Q, we know T, and we know Q initial. Okay, so we can just put those numbers in and solve for K. And when we do that, we get 1.8 per molar per second. Okay, so we're just plugging in those numbers here to get 1.8 per molar per second. And remember, for a second order rate constant, the units are always per molar per second. Okay, so now let's go back to this, to having data and finding the rate law based on the data. All right, so we're going to graph three ways. We're going to graph concentration versus time. We're going to graph the natural log of concentration versus time, and we're going to graph the inverse concentration versus time. We're going to determine which one is linear, and then we can determine if it's 0, first, or second order. Okay? All right, so here is our data. So we have the reaction of A going to two products. Okay? And we're going to look at the concentration of A over time, and we can plot that. All right, so here the concentration of product, we know we have 2 times product that forms. And so here we are going to look at the natural log. So we have the concentration of A, we already have that. We have the constant, and we need to find the natural log of the concentration of A, and we also need to find 1 over the concentration of A. Okay, so we're going to do that so that we can plot each one of those versus time to determine what is the order of the reaction. All right, so here we are, concentration versus time. To me, that does not look linear, so we can say right away, all right, not 0. Okay, that is not linear. No way, no how. Okay. All right, then, okay, so this is a little closer when I plot the natural log of the concentration versus time, but still not right on that line, is it? So we can say, nope, not first. Okay, well then let's try second. So if we take the inverse of the concentration versus time, it looks to me like I have a line. And so I can say that this process is second order, okay? And my rate constant here is 0.1 per molar per second. My rate constants of K are always per molar per second for a second order reaction. Okay, so we found that our reaction was second order because it was linear with the inverse concentration versus time. And so now what we want to do is we want to find out what is the rate. And so we can take our rate constant, we can take our concentration squared because it's second order to find our rate. All right, and so now let's look at the relationship between order and half-life. So for a zero order reaction, the half-life is the initial concentration over 2K. For a first order reaction, it's the natural log of 2 over K, which is 0.693. And for a second order reaction, we have 1 over K times the initial concentration. So both zero order and second order have a relationship with the initial concentration. First order does not when it comes to half-life. All right, so let's do a half-life calculation. So here we have molecular iodine dissociates at 625 Kelvin, has a first order rate constant of 0.271. What's the half-life of this reaction? Okay, so we know what the rate constant is. We know that there's a relationship between the half-life and the rate constant. So this is given as a first order reaction, therefore it's 0.693 over K, and we know what K is. So we can solve for the half-life. And so notice K is in per second here. That means that our half-life is going to be in seconds. All right, so let's do another example here. So here we have the reaction of Q going to 2R, and it is second order in Q. Okay, so it's second order in the reaction. We have the initial concentration. We're given a rate constant. We're going to find the length of time it takes to get from 1/2 the initial concentration to Q. Okay, so this is a half-life question. All right, so what we're given is the initial concentration. We're given the rate constant, and we want to find the half-life in seconds. Okay, so we're going to use the half-life equation for a second order reaction. So we're going to take 1 over the rate constant times the initial concentration. And really, we're just plugging in those numbers here. Okay, so we're going to take 1 over the rate constant times the concentration, and we get 56 seconds. So it tells us that the half-life of this reaction is 56 seconds. All right, so that's the end of this video on using those integrated rate laws and finding those orders of reaction. Thank you.